Let's get started now. So today it's a pleasure to have Professor Coriel Her with us. He's from Yale in the Department of Mechanical Engineering, Applied Physics, and Physics. And he got his training in condensed matter physics at University of Pennsylvania, and then at UCLA and Chicago for postdocs. So he is very well known in the soft matter community and has served in some leadership positions, such as the chair of GSMP, that's the American Physical Society's statistical and nonlinear physics group. But today we're going to hear about metals. That is also a glass forming material. So I'm looking forward to that. And of course, all yours.
Thank you. So I welcome questions. You can interrupt me at any time. The more naive the question, the better. That'll make me talk more. The other thing I want to mention is I'm talking about the glass formability of binary alloys, but my group is very broad. So I study, cell motion, I study emulsion droplets, and the reason why is because I'm not really wedded to any particular software or computing platform. And I think that that is a benefit. And so, especially for the younger students, think about that as you're progressing. So one thing about Yale, I invite you all to Yale. I'll show you around. It's small, so we have to collaborate, and collaborating is good. So I have to do something that's a good thing. And so I'm in multiple departments, and that means basically I steal all of their students. My primary appointment is in engineering, so I get a lot of engineering students, but I get a lot of physics students as well. Mark Shattuck is a colleague of 30 years. He was my PF in electronics as an undergrad when I was a physics major. And don't ask him whether I know electronics. But he lives in Connecticut, and we collaborate a lot. And
then, that's like a TA or?
Yeah, we called it a teaching fellow, but I think back then we called it a teaching assistant. So yeah, TA. Yes. He was my teaching assistant. He was the graduate teaching assistant at Duke University, where I went to undergrad. And so the work I'm going to talk about is over the last sort of 5 or 10 years in this area. It was originally part of an NSF MERSEC, where Jan Schroers is an experimentalist at Yale who worked with Bill Johnson around on bulk metallic glasses. He is very good at developing new techniques in making and characterizing metallic glasses. And so that's where this work originally started. And then more recently, we have a training grant in this general area. I think some of you know Wei Wei Jin. He's an awesome postdoc, and he's done a lot of this work. And then Jinpeng Fan is a PhD student, and Yuan Xiao, who I call YC, is at a new laboratory that you and I visited this past summer. So just a quick smattering of papers. Hopefully you'll go home and read all of them. But the general idea is that I'm interested in the glass formability of materials, and in particular alloys. But I'm also interested in the mechanical properties. And a key question, which I've talked to a lot of you about, is that an amorphous material, be it a granular material or a metal, it's amorphous. But it will deform in particular ways. And there's this idea, can we define defects in amorphous materials as we do in, say, crystalline or polycrystalline materials that control the deformation of the system? And I would argue yes, and that's a question that we're working on. So a few slides about motivation. I don't need much motivation to study metallic glasses because I'm generally enthralled in amorphous materials. Why do they occur? How do they occur? But from maybe a material standpoint, they do promise some interesting or important structural features. So one is their fracture toughness can compete, doesn't always, but can compete with steel, and their yield strength can compete with steel. And so if we can find out how to make better metallic glasses, they may become relevant for structural materials. Another interesting area is maybe in sort of resonators and nanoresonators, is that they, under many conditions, say in the upper left, they can have high quality factors that can be used in sort of nanomechanics applications because you can tune them to have high quality factors. I'm going to show you two examples of sort of the underpinnings of the general area. The general area is alloys. That is, you have pure substances on either end. So like in this case, I'm talking about a copper nickel system. And then the general question is, what's happening in the middle? You know, it's neither nickel nor copper. And so what's happening in the middle? Does it form interesting phases? Is it glassy? Questions like that. In the case of copper and nickel are sort of sufficiently similar that nothing happens in the middle. You just sort of smoothly transition from nickel to copper, and it's all FCC, and this is not very complicated. But then sort of a typical example of something that's sort of non-trivial is the case of nickel aluminum, is that you don't sort of smoothly transition from nickel to aluminum. You have sort of new physics that happens in the middle. You form these BCC crystals, and nickel is a FCC material, aluminum is an FCC material, and then in the middle you have this nose of stability for the BCC phase. And so similar questions happen with glass variability. What is the glass variability and sort of the middle regions of these phase diagrams? In general, what we're going to do in the sort of computational studies is we're going to do cooling. You could do heating. We're going to do cooling. So we're going to take a melt. We're going to take a disordered liquid, and we're going to cool it at a certain rate. That is, we're going to suck temperature out of the system, and we're going to see, does it crystallize during that process? And that question depends on rate. So on the one hand, everything is a glass. If you cool it fast enough, it will form a glass. If you cool it a little slower than that, it will crystallize. And so here's a demonstration of that. This is pure nickel and embedded atom potential, and temperatures on the horizontal axis, the densities on the vertical axis. And you can see the crystallization happening with these rapid increases in density. And so this arrow represents cooling. I'm starting at a high temperature and I'm cooling. This arrow represents, I could also do heating from the crystal phase, and then I could melt it. You can see from the cooling curves, there's sort of a transition that happens at 10 to the 12 versus 10 to the 13 Kelvin per second, these enormous rates. If I'm blue and I'm cooling at 10 to the 12, a relatively slow quench, then I undergo this abrupt transition, crystallization, and my density has a corresponding increase. But if I cool at 10 to the 13 and all subsequently higher cooling rates, I will bypass that and I will just, have form this glass. And so this question raises, what is the critical cooling rate? The critical cooling rate for pure substances is typically very high. And so that's captured. Well, let me first just show you sort of how these are done. This is at the fast cooling rate, and this is at high temperature. I'm cooling it, I'm cooling it, I'm cooling it, I'm cooling it at this relatively high rate, and then eventually it will go to very low temperature. And I may have a couple sort of local regions that are relatively ordered, but on the large part, this is a disordered sample. Then when you go to the slower rate, you'll have this, first order like phase transition where you crystallize. So I'm cooling, and then remember that blue curve, and then everything sort of locks into an FCC phase.
And it's symmetric if you're heating, where that happens is at the same point.
It's not at the same point, but that's the difference between sort of liquidus and solidus, and you can basically keep track of that difference as you tune the rate. So in this case, if I'm truly in equilibrium going really slowly, they would occur at the same spot. But because I'm going at finite rate, it'll be a little bit asymmetric. But for this study, I'm not going to deal with that interesting detail. I'm just going to always do cooling, and then it's just this one case.
Yeah, I was just have a question at the previous simulation. There are several colors.
Thank you.
They're all located on a specific particle.
Yeah, so what I'm gonna do in general is what you see on this former slide is everything turned green. And what that meant was everything was an FCC-like atom. And so what I ideally want to do is associate an order parameter with each atom. And I'll tell you a little bit more detail about how that is, but it's basically what type of local order do I have? How many neighbors do I have? Are they close? Are they in the right orientations? And you see in the one that was cooled fast, most things were disordered, but there are a few that sort of looked like they had some crystal order, but in general.
That was the part that kind of confused. No, brings up my curiosity because how can we localize structure to a specific particle?
Yeah, so the way you do it is you just say, I'm a particle, and what are my neighbors doing? Are they in the right positions?
I see.
And so still a little bit generally, I said everything is a glass. Everything is a glass. You just have to cool it fast enough. And so this is a library or reference for how fast you have to cool different materials. So people may not still believe this, but even pure substances can be cooled fast enough to form at least nanoscale glasses. This is from work in China by Weihua Wang. And but then this was a binary bulk metallic, or at least metallic glass former. There's water, a bulk metallic glass former here, and then silicon dioxide. And so you see what's happening as you go from these materials to these materials is the critical cooling rate is decreasing. That is, what cooling rate do you need to achieve a really large crystalline order? And I'm going to talk more about what this is. There is a corresponding relationship between the critical cooling rate and how big the material is that you can create, which has to do with sort of fundamental properties of heat transport and conduction and diffusion of heat. So just for your just to get it out there, there are binary and ternary alloys that have been characterized in terms of their critical cooling rate. So the binary systems are here. You can see that people have, so copper zirconium 50/50 is a pretty good glass former. That is, it has a critical cooling rate of 250 Kelvin per second. So it can withstand really low cooling rates and still be glassy. And so this is sort of what we know already. There is kind of a funny issue in the field, which is probably pervasive in other fields, is that positive results always trump negative results. So we have this data on the positive results, but we have no data on the negatives. There are many more negatives, like those systems that don't form glasses, but no one publishes that because that's not a positive result. And then we can characterize the ternary systems as well. One thing that you may have caught on the right side of that table is me starting to try to come to grips with what controls the glass variability. Is this something I can understand? Is this something I can interpret? And so one thing that is going to be important is the size ratio. I think everybody knows that if the particles are the same size in 2 dimensions, 3 dimensions, 4 dimensions, whatever, they have a greater tendency to crystallize. So one thing that can frustrate crystallization is that the sizes are different. In this particular way, I'm plotting it, I'm saying it's the diameter of the small atom divided by the diameter of the large atom. And so it's by definition less than 1. And so if this number is close to 1, then it's not a very good glass former. Then the other thing that may be important is what's the fraction? So you have 1 is small and 1 is large, but how many of the smalls do you have? How many of the large do you have? And probably you could guess is that you probably want them, you don't want an overabundance of one over the other, because then they can sort of segregate. So here I just show you, I put the data that I had on the previous plot of the glass formers, so I just scatter them on this plot of just these 2 parameters. And so they cluster into generally 2 categories, at least in binaries. They cluster into this region and this region, and these are the metal, sort of the metal metalloid and the metal metal. I can explain these, but I'm not going to focus on them today. I'm going to try to argue why is there a cluster here. Yeah.
I have a question. What about there being an overabundance would cause them to segregate?
I don't want to spoil this secret, and so just wait one more slide and then
Okay.
definitely ask again. I didn't. It's like in 2 slides.
Can I ask one question?
Oh yeah.
You show the size ratio on that y-axis, and that those numbers aren't very different from 1, right? The smallest is 0.6. Is just because I'm not in this area.
So this captures everything.
Okay,
So there's
so you
not.
don't have-
So it's not 2 to 1. It's not. These capture the region of the periodic table that I want to be.
Oh, okay.
But that's a great question because I am interested in alloys, so I want to, understand whether my features, capture alloys.
Sure.
So this is what I want to do. I'm basically going to cool these things. And the first model I'm going to study, which my reviewers say never do, is I'm going to just basically think of repulsive particles that are cooling. Pairwise repulsive particles that are cooling. I don't know if you thought about it, but as long as the range is short enough, that is, they don't interact, like they're not sort of charged particles, as long as they interact at a short enough range, it's the same as hard spheres. And please ask me after the talk, if you don't believe that, talk to me. I'm not saying that charges, like Coulomb charges are hard spheres, but if the particles interact at a short enough range and they're purely repulsive, they are hard spheres. Okay, that's what I'm going to study. I'm just going to study how hard spheres form glasses.
So do you care whether you study it in 3-dimension or 2-dimension?
I'm doing all 3D. I think that is an interesting question because basically, as you go to higher dimensions, the glass forming ability improves.
Yeah.
So 2 dimensions, 1 dimension, everything is a crystal because you can't move away from your neighbor. In 2 dimensions, it's really hard to not crystallize if you have particles. And so 3 dimensions is a little easier to form a glass. 4 dimensions even easier. But I'm not going to talk about 2 dimensions, but I know why you're interested.
Yeah.
The way that I characterize, I need to know when I do my quench, when I cool the system, do I have a glass or not? So I need to characterize the order in the system. That's a long story and everybody has an opinion. I'm sure you has an opinion. But it's not that controversial. So one way I'm going to do it is the central particle is yellow. And I want to, if I'm in an FCC lattice, the 12 neighbors have particular orientations where they have to be in phi and psi in a spherical coordinate system. And so I'm going to create a function that weights that the highest. So it's like this order parameter is going to be 1 if all the atoms around me are in an FCC lattice, or it's not quite 1, but it's relatively high. And then it's going to weight them low if they're not in that, like if they're in random orientations. And then what I want to do is, one way you can do it is like have a cutoff. If my bond orientational order is pretty high, I'm crystal. But you can do a more sophisticated way where you look at correlations between the bond orientational order with this atom and then another one. And then that's a little bit less, I don't want anything to be sensitive to my cutoffs. So we do a more sophisticated way of looking at correlations between what my current bond orientational order is and what is a neighbor. And if it's those correlations are high enough, I'm in a crystal-like environment. And then I say I'm a crystal.
So is that capital Y your weight?
This is actually the YLMs from quantum mechanics. And so these LM are basically, let's see, I'm looking at Q6. So this is the YLMs will be the largest if the I and J's, so the I is the central particle, the J are the neighbors. The YLMs will be the largest if the theta IJs, which are the spherical coordinates. And so if they're in the right positions, then this YLM will be largest. Why do I need YLMs? Because I want rotational invariance. So I don't want it, if I'm in a crystal at this orientation, I still want to be relative, I want to be high. So that's why I need to, sum over the M's. So this sum is over neighbors of I. So it makes sure they're in the correct spherical coordinate positions. And then this one is summed over all particles. So I look at a total Q. And if this Q is large, then I have a relatively crystalline sample. So for example, if everything was in an FCC, if I had a perfect FCC lattice, this would be a high number. It's going to be around 0.7, just the way it's defined. Whereas if I'm in a random environment, this number is basically 1 over the square root of n.
So you said this is in spherical coordinates, this like,
So spherical coordinates that are embedded at relative to the central atom.
and there's no radius in your spherical
Oh, and
coordinates?
yes, that's an important point. So everybody says, well, what is my J? Like, is my J is my neighbor.
Mhm.
Do I care about and so this is typical, so everybody, this is where people have opinions. Well, I think it should be this distance. And so one way to do it sort of relatively without a cutoff is to do a Voronoi tessellation.
Mhm.
So you do a Voronoi tessellation and then that unambiguously defines the neighbor by, do you share a face? And then there's also face weighting that you weight those neighbors that have big faces, so you're really close. Whereas if some neighbor further away, it has a very small face. And so you wouldn't weight it as much.
Okay, so your R is kind of like thresholded, so you don't have like.
So my neighbors are well defined, that my J's are, are first neighbors of I. Because if you averaged over every J, you wouldn't get anything.
So is this essentially giving you a packing fraction?
No, so that is important. This is getting are my neighbors in the correct, in crystalline positions. It's relatively independent of packing fraction because you can do a Voronoi tessellation for any packing fraction.
Okay.
But you can define local packing fractions, which could be interesting. So based on what I just said, you can calculate fraction crystal. So every atom is determined crystal-like or non-crystal-like. And so then you say, count up how many are crystal-like, you divide by the total number of atoms, you get a fraction which goes from 0 to 1. And then you measure this as a function of different cooling rates and here in different systems. And so here's one system, it could be nickel. And then here's another one, it could be aluminum. And so here, it says if I go to high enough cooling rates, I'm amorphous. If I go below the critical cooling rate, I'm crystalline. And so you can basically read off the critical cooling rate, by saying, where is it hit 0.5? That's the critical cooling rate. So the procedure for measuring the critical cooling rate, at least in these simulations, is sort of straightforward. I'm interested in what determines that critical cooling rate. I finally get to your question. So one feature, so then you're interested in what features determine this critical cooling rate. Well, getting back to what we originally started with, is these purely repulsive particles, it's basically how things pack. So if I have too few, like here's a majority species blue, and there's some minority species yellow, they're significantly different sizes, but there aren't enough of them to disrupt the crystallization. Same thing here. Same thing here. But then you get enough yellow particles that are a different size, it disrupts the crystallization. And so this one is a good glass former, whether it's these or not. And basically, for these types of interactions, it's impossible to form, you cannot form glasses at 20% or 80%. You have to form glasses in the center, because that will cause this frustration. And so these are the measurements. So the critical cooling rate as a function of the number fraction of small or different sizes. So let's start at 1. That's the easy one. If the sizes are the same, then the critical cooling rate doesn't depend on the fraction of smalls. It's just a pretty bad, crappy, it's a crappy glass former. But then as you increase the size ratio, you start to form better and better glasses. You start to get this really deep nose. But the cool thing is, where does that nose occur? It occurs, roughly speaking, at equivolume. So this is that idea again. You need enough particles of both species in order to disrupt. So if the small particles take up less of the system, we'll just make them equal volume, and then they'll take up enough of the system to cause this disruption in glass forming ability. So this line right here is equivolume of the small particles. And so one way to form a glass to get really low critical cooling rates is to do this roughly 50-50 different sizes. And so, people have known about this for a while. And so this is just a prettier picture where I'm putting the small, it's the same data on the previous one. It's just I put the fraction of small on the horizontal axis, the size ratio on the vertical axis, and then I put the glass variability, the critical cooling rate, and the color. And then you have this bullseye, which is a really low critical cooling rate happening right here.
So there's a question on Zoom that says if you use periodic boundary conditions, then the critical cooling rate is only limited by homogeneous nucleation. But in experiments, there's normally a interface with like a solid. So have you looked at heterogeneous nucleation that interfaces?
I have not looked at heterogeneous nucleation then. I would say that is, practically speaking, probably very important. But I would say the interesting question would be, with homogeneous and heterogeneous nucleation, which, I can get good glass formers with competing with homogeneous nucleation. I can get glass formers with competing with heterogeneous nucleation. So it's a question of, do I want to model this particular experimental system? Then yes, I would need to do that. But I'm just talking about the general features of glass variability. It doesn't seem particularly relevant to what I'm talking about.
Professor, do you mind to go back to the previous graph? I just remember it's just a naive observation that at the ratio 0.5, the curve, it seems that the maximum is not the same as the equivalent curve.
Yeah, so a little of this is non-monotonic. So what's happening is you're becoming a better glass former, obviously, when you go to 1 to 0.9, 0.9 to 0.88, 0.8, but eventually it is not a better glass former. That's reflected here. So you become a better glass former, you're the best glass former, then you become worse glass former. And that's because the size difference is too big. So that will give rise to segregation as well. So if there's any way in which the smalls and larges can separate, they will. And this starts to get to that region. Like right here, you're 2 to 1,
Right.
which is pretty big. So there's a special region. Okay, so that is known. There's Inouye's rules. So empirically and through experiments, people know generally what gives rise to good glass variability. generally speaking, and one of those is what I just said. But let's keep going, let's try to make it quantitative. You'll see what I mean in the subsequent slides. So another model that I can do, as I just said, purely repulsive systems, as long as the range is not too large, are hard spheres. Hard sphere in binary systems, I just did the entire model. There's nothing else to do. I varied the size ratio and I varied the number fraction. There's nothing else to do. So now I literally need to go to a new model. So the next possible model is a system that's not just repulsions, because I just did all the repulsive models. So I'm going to add attractions. Now when I add attractions in a binary system, I don't just have one attraction, like I have A and B, or large and small. And so there could be attractions between A and A, there could be attractions between B and B, there could be attractions between A and B. One thing that I want to emphasize is I'm currently talking about sort of microscopic parameters. That is, like they're on the scale of the atom. Eventually, I want to get away from that because that's really hard to measure. Like I'm interested in the features that control the glass variability. Eventually, I'm going to be interested in like things that I can measure from maybe a bulk experiment. And I'm going to have to get away from this. So right now, I'm still going to do it. So the next level model that I could do is like a Leonard-Jones interaction. So there's cohesive energies between the A's and B's. There's like a heat of mixing or a relative, like how strong do the A's and B's interact? Do they promote mixing or do they not promote mixing? And then there are the atomic sizes. In this model, that is everything. And in general, what you'd be interested in is I want to know the glass variability of all of those parameters.
So at an atomistic sort of level, what is that cohesive energy physically?
So the cohesive energy, you can think about it a couple ways. One way is it sets the scale of the thermal stability of the crystalline phase.
Okay.
But you could also define it
But there's gotta be some surrogate for
Another thing
actual atomic structure. Or something that.
well, let me just give you one more to see if that it helps. Is you could have a cluster of atoms. You say, what is the energy required to take one of those atoms and take it to infinity? It's a cohesive energy, but it's basically the thing that sets the scale of the cohesion of the solid that you're forming.
Is this something that's well known in character?
Yes, that they, yeah. But the one thing that I want to get at is this thing that I'm talking about is at an intermolecular potential. That's not what people are measuring. Now the question is it like one-to-one with a macroscopic thing that I'm talking about? I don't, we need to talk about that further. But within this model, I'm talking about literally the interatomic interactions.
So you do like AFM or something to measure?
Well, no. So let me hold that off to being fitting to a few parameters. But in this is a simulation. I'm in control of how the atoms interact, and I'm gonna simulate that. So I want to get at this because I keep want to pushing on this, is that for this model, the glass variability, like in principle, is known. It is what it is. It's like you measure the critical cooling rate, and these are the only parameters in the model. I made them look a little fancier. Like now this is the size ratio. This is I made them dimensionless. So this is the size ratio. This is the fraction of the A's. This is the sort of mixing energy, and this is the cohesive energy, but I don't really care about the overall cohesive energy. I only care about the relative cohesive energy. And so I took the difference and divided by the average. This is known, you can measure it. And so that's what I'm going to do. But what I'm getting at is the glass variability, you can literally measure it. And what are the features that it's a function of? You'll see why I'm pushing on this. So I'm going to show you two slides. They're sort of heat maps, and then they look very similar. This one is I'm varying the fraction of the A's or B's. In this case, I'm varying the fraction of the B's. And I have to I'm plotting the glass variability, which is in the color. So the darker the color, the better the glass variability. And try to, in your head, try to think from the general principles already said, where should the red be? Like, the first thing is in the upper left, there's not much red. Well, why is that? Well, there aren't enough A's. So you already know that. The upper left should be basically blue. There aren't enough A's. You already know that. And then when you're sort of in a middle region, when you have enough A's, where should the red be? Well, I'm looking at the difference between the cohesive energies. So you can't get a glass if the cohesive energies are the same. If the cohesive energies are the same, they're both the same. So why would it form a glass? Same thing with here. You want epsilon AB to be relatively large so that you encourage mixing of the A's and the B's. So in general, I just sort of hand wave that in general, the glass variability is going to be on the right. The bad news about this model, which is related to what Jesse was asking, is the features, the binary alloys occur in this nose. This nose is repeated. So in general, this is not, a quantitative model for metallic glasses because the nose is happening right here. But what that slide is I wasn't varying I was varying all the energetic parameters and I wasn't varying the size ratio. And so does anybody know, if you're allowed to vary the cohesive energy, so you have a mixture of A's and B's, you have the cohesive energy, and you have the size. Do you want the larger size to have the larger cohesive energy, or do you want the larger size to have the smaller cohesive energy? And the way to think about it is, again, you want to maintain differences between the A's and the B's. So the answer is that the larger size has to have the larger cohesive energy. If you don't do it that way, they will pull each other in and they will make the particles look more homogeneous. And so in this model, you want the larger cohesive energy to be larger sizes. And so with that, you get this interesting effect. Again, I'm showing you the critical cooling rate, or all the colors. You can see a huge asymmetry between basically when I change the size. Does the larger size have the larger cohesive energy, or does the larger size have the smaller cohesive energy? And so this model has really bad glass variability. But the others have good glass variability. And this is true for roughly 60% of good glass formers and alloys. So it's sort of one aspect that's not in the original Inouye's rules. Okay, the other thing that I wanted to mention is we should solve the models. What I mean by solve the models is we should find the glass variability as a function of the entire parameter space. Because you can, and that's what I want to do. And then you could start to understand which features are important. If you solve the glass variability for every parameter, well, then you know which features are important. Basically, I've already done this for this model. Like, here's the glass variability as a function of the various parameters in the model, and I've sort of told you these general principles. You want the systems to mix, you want the cohesive energies to be different. There's this interesting effect that when you have larger particles, you want larger cohesive energy. So in general, we have solved this model. To prove it, basically I can collapse the glass variability. So believe me, I can plot the glass variability as a function of a parameter and it collapses. That in general means that I've solved it because I know exactly what the parameter dependence is. And so in general, this is really nice. I can tune the glass variability of this system over 8 orders of magnitude. And I know exactly how it varies. So let's go a little more realistic. The unfortunate thing is that, well, unfortunate for me, I guess, is that metallic glasses aren't Leonard-Jones particles, unfortunately. They depend more like this. So this is actually real data. This is the critical cooling rate versus various features. So this is experimentally measured. And then the data points, are taken from encyclopedias on metallic glass formation. And so on this axis is a ratio of the variance of the particle size. So this is the variance of the constituents of the alloy that I have, normalized by the average and weighted by the number of elements. And so as I move to the right, I have larger variant, I have alloys that have different sizes. And so you can generally see that there's a correlation between glass variability and size. So that's sort of the good news. The bad news is it's not one-to-one. There's clearly, it's a higher dimensional feature space than just this. Then it gets worse. But now I try to add energetic features. So I'm adding in the difference of the cohesive energy of the elements that are included in the alloy. And so you have the critical cooling rate versus that same parameter about the variance of the atomic sizes, and the color is the difference in the cohesive energies. And you see basically in general, there are some yellow, down, which would be supportive of what I'm saying, that you need cohesive energy differences that give glass formers, but it's kind of spotty. So we haven't nailed it with these. Was there a question? We haven't nailed it.
Yeah, I was just wondering, are these experimental, like what you've shown so far, are they experimental results or computational, or like what? I think you said some of them are like Leonard-Jones.
So the nice thing about this model and all models, it's not necessarily that it reflects reality, it's that I know the dimension of the space and I know the features that govern that space. The glass variability of Leonard-Jones mixtures is a function of these 4 parameters, and I can measure it for that 4-dimensional space. So
Okay.
I know exactly what it is, and I know which features are important and what combinations they need to be given.
Okay, so
This data is real data. So the pros and cons of real data are, it's real data, that's the pro.
Yeah.
The con is I have no idea how big is the feature space. Is it 100-dimensional? Is it 4-dimensional? How many features do I need in order to predict the glass variability? That's why Inouye's rules were there. They're like, well, you should have atom sizes that are slightly different. You should have different cohesive energies. You should have a certain heat of mixing. You should have more elements. I'm audacious and I'm bold. I want to know the quantitative. I want to know more. And I have 15 minutes. So this is what I'm getting at. What features determine the glass variability of alloys? Now this is where I'm talking about atomic versus macroscopic. When I was talking before with these Leonard-Jones systems, it was more atomic. Like I told you exactly, well, these atoms interact in this way, but I'm not necessarily going to be able to do that with every alloy. I'm not going to know, maybe I could do density functional theory, but maybe you want to know, how does the glass variability of this alloy depend on the elastic constants at 0 temperature? How does it depend on the melting temperature at every concentration? More macroscopic, but I want to start making a list and crossing them off and understanding each one. So I'm going to need a mapping between microscopic atomistic features and these. And that's an embedded atom potential. Then we develop an interatomic potential that will allow us to vary these features so that we can determine the GFA as a function of features. So that I can basically, I have that, I have the crystal symmetry. So the competing crystal phase, my model captures the competing crystal phase. My model, so I've included that. How does the glass variability depend on it? Now I've matched the elastic constants at 0 temperature. I've done both. How does the glass variability depend on that? So on and so forth. So this is by far not exhaustive, but this is sort of a very crude summary of the current state of how do I computationally determine the glass variability of an alloy. So there's a bunch of crazy people who say, well, I'm going to look at pair potentials. Well, That's already been done, so we just did that. We basically know the glass variability of all pair, it's not all pair potentials, but a good parameterization of pair potentials. Then people go to many body potentials. The problem I have with many body potentials is the 30-40, the glass variability depends on all of those parameters. That is, you need to develop an embedded atom potential for each alloy system, each concentration, and so the glass variability is going to depend on those parameters. Now, it's going to depend in such a way that they sort of model the elements, but we're interested in general features of glass variability. So, one thing that's bad about pairwise interactions often are in the crystal phase of metals, the elastic constants have been measured and they're anisotropic. So the C12 and C44 are different values. Pair potentials do not give that. You can have anisotropy in pair potentials if the structure is disordered, but if you measure the elastic moduli of pair potentials in their crystal phases, the C12 is equal to C44. The other thing is that a lot of pair potentials form FCC, and you can't get other crystalline phases. You can with pair potentials, but you'd have to specially design them. There's like Zugatov and things like that. So the bad things about, say, an embedded atom potential are interpretability. You have these parameters that match, various experimental results, but which of those features are important? I have, okay, so the reason why I got into this business is I have about 5 to 10 slides on experiments that are really cool, is Jan Schroers has these combinatorial sputtering techniques where he can shoot elements at a wafer. And based on the relative abundance, so you basically have a wafer and you have different positions on the wafer. At different positions, there'll be different fractions of atoms from each of these guns that reach that part of the wafer. And so it's a way to tune continuously the concentrations of each element. So in this case, it's a 4-component alloy, and it can continuously tune the concentrations. And so then he can basically take that wafer and do X-ray scattering on it and determine whether it's, if it's crystallized and what is the crystal phase, or is it amorphous or things like that. So this is I spent lots of hours preparing this slide. Now, so this is, I write it this way because it's a schematic idea, so you get it across the schematic. Again, I have the critical cooling rate, and then I have the fraction of B. So 0% B, 100% B. The combinatorial sputtering technique is like a single slice in the critical cooling rate, or the single slice in the cooling rate. That is, when these guns are going off, I'm not continuously changing the rate at which I'm depositing the elements. So they're done at a certain electronic potential. They're accelerated and they're hitting the target. And so I'm doing horizontal slices. And then the material has its critical cooling rate dependence that I've shown you for each material as a function of A and B. And so what the sputtering can get is the window of the amorphous range. So here, at this rate, I'm below the critical cooling rate and I will crystallize. Here, I'm above the critical cooling rate, I will form an amorphous phase. Here, I'm below the critical cooling rate and I will form a crystal. And so what I can get is the range of amorphous structures. And so the better glass formers are the ones that have a bigger range. And obviously, if you don't have a range, you're not a good glass former. Can you see this in the back? So this is his data. This is the fraction of A, fraction of B. And the dots represent the results of the X-ray scattering. And he has this color code. There are some mistakes in there, so don't pay too much attention. You can ask me later. It's like, these are, AM means amorphous. So if you see them, I'm colorblind, but I think if you see black or red, it's forming, amorphous phase. And then if it's, BCC, FCC, it's forming these crystalline phases. And so in general, the crystalline phases appear on the edges. The amorphous regions will appear in the middle. But what's cool is, look at all this. You have all this data and you can try, but what should I do? Should I use an embedded atom potential? I mean, I will. Should I basically develop embedded atom method potentials to study all of these materials? Or should I try to or should I do both? I should try to get general features of what controls the glass forming.
Throw it in a neural network.
Throw it in a neural network and call it a day. What I'm gonna do is, I just have sort of five minutes left, but one system that we're studying as like a benchmark, and we're not quite done yet, is we're looking at the copper, nickel, aluminum, magnesium. So what are all the possible binary alloys from those four materials? And this is what they are. The copper nickel is boring. Basically, any model you use, you can predict what it is. It's copper and nickel are so similar. Nickel aluminum starts to become very interesting, and you can start forming amorphous phases for these final form. So this is what they look like. Again, I said copper nickel, very boring. At these cooling rates, you just form FCC the whole way. Copper aluminum, we're not fast enough to form an amorphous phase, but then basically starting with nickel, aluminum, copper, magnesium. One interesting thing why we studied this system is you get this magnesium, if it's pure magnesium, forms HCP. And so you can start to see, well, what happens is, do I have a better glass forming material if I have different symmetries on either end?
On the last slide, the AM means amorphous, right?
Yeah.
So when something says like HCP plus amorphous, like is that like or it could be both?
Yeah, so in general, they're mixing models. So what we're doing is we have an X-ray structure factor. We don't have images of the material. The image that we have is the X-ray scattering function. So what you have to do is come up with a model to match the X-ray scattering. And so what you can do is say, I'm gonna have a mixture model. I'm gonna have fraction of the system is HCP, another fraction is amorphous. And then you can sort of solve for the correct proportions. So wherever it has a plus, that means it's a mixture model, and I solved for the proportion that matched that X-ray scattering. But they usually make sense because it's like HCP over here, it's amorphous over here, and then there's a mixture in between. So what I'm gonna quickly go through is that basically EAM simulations do a pretty good job. So here's copper nickel, nickel aluminum. They do a pretty good job because they do a pretty good job. I mean, they were fit to the crystal structure of the underlying equilibrium phases. So for example, we don't have to worry. So like here's the interesting case I was talking about before. Nickel and aluminum are FCC at the ends, but then they have an interesting BCC phase in here. Well, that was built in. When you built the EM potential, you built that in. So we know that that's going to happen. So just click through these. So here's a summary of the results from the EAM potentials, and generally I agree. The problem that I have with this is, well, am I just going to go do the rest of the periodic table? What did I learn? Jesse says give to machine learning. Yeah, I agree. Sorry, I'm sorry. I apologize. So, these are all the results, and they generally agree. The experiments occur here, and they're showing basically that the aluminum magnesium is the best glass former. than copper, magnesium. The nice thing about that is it's sort of showing this rule that if you have different phases on either end, that suggests that you're getting sort of more competition. Like you have HCP on one end and FC on the other, that leads to frustration, and so these are sort of the better glass formers. And then nickel aluminum is just sort of kissing the experimental cooling rate. So in general, this agrees. The question that I ask is, well, what did I learn? One thing you could say is, well, I simulated these materials. Did you really? So in the last 2 minutes, what I'll say is, here's another method, a similar but related method, is build a minimal model that teases out the features that could control the glass variability. So one thing that could be important is that the anisotropy and the elastic constants can only be obtained by a many-body potential. At least that's one way to get it. So we could test, is that important? Is anisotropy and elastic constants important for the glass variability? And so we can build 3-body potentials. So one question that I think is interesting is, why do we need many-body potentials? So let me just quickly go over 3-body potentials. So these 3-body potentials, a very famous one was Stillinger-Weber when he modeled silicon and germanium in the 80s. And so these potentials in general are pairwise potentials plus a 3-body potential. The 3-body potential classic is like a cosine, where you have that the potential depends on the angle between 3 atoms. And so we have a pairwise potential that's parameterized basically by P and Q. P and Q can basically control the shape of the interaction. Then the 3-body is controlled by lambda and basically G and one of these thetas. And so at the end of the day, what we have are the pairwise parameters are PQ, 3-body parameters are lambda, gamma, and GS. And this was what I was saying about all this song and dance about microscopic versus macroscopic. So these, since they're based on my potential, are microscopic. They're based on the interactions between atoms. So what we need to do is the mapping between microscopic and macroscopic. And this is what embedded atom method potentials do all the time. But at least now we're like controlling the number. So right now with these, we can fit the elastic constant. We have 3 elastic constants, a lattice constant, and a melting temperature. So then I can say, what is the glass variability as a function of all of these? And then I could ask, well, it doesn't really depend on the elastic constant anisotropy, or it does. And then we would learn something. So we've started doing that. We've basically calibrated to the pure systems. So they form FCC for copper and nickel, that's sort of trivial. We've started doing the mixing terms between copper and nickel. And I just can show you a failure is that this is the nickel aluminum one, is that we weren't too careful about how we did the mixing model. And then in nickel and aluminum, the BCC phase comes in. And so you apparently have to do something special in order to build in the BCC phase at intermediate concentrations. You can't just sort of do a straightforward binary model. So with that, I will go through my conclusions. The thing that I'm advocating is a more stepwise approach. I've clearly shown, at least for the trivial potentials, that the glass variability can be completely specified in terms of a low dimensional feature space. That's how the models were built. I think a room for growth and understanding is when we jump to embedded atom potentials, we now have 40 parameters, which means we have a 40 dimensional feature space. It's hard to understand. And so there may be a middle ground where we can develop 3-body potentials and study the glass variability as a function of sort of what I said, the melting temperature, the elastic constant anisotropy, the lattice constant, things like that. The nice thing is that we have this data set where we know the the critical cooling rates, the glass variabilities of a large set of binary alloys from Jan Schur's. And we can maybe come up with design principles for how would we better make metallic glasses, and then of course this can go on for 10 years and we can study ternary systems. So I thank for all your questions and paying attention to me.
Any last minute questions? Oh, thank you.
So how much of this like experimental work is to understand how this glasses form versus like identifying good glasses? Like if you could identify a good one, but you didn't know how it worked, or like what exactly how you should choose the parameters, you just identified like good glasses. Would you consider that a success, or is that not?
I think both, it's a good question. I think both need to be done. So definitely from a technology standpoint or grantsman point of view, you have to find good ones. And it's not really about, if you had a method that you didn't understand and you were able to find them, that would be good. But my worry is that it's gonna take so long to do that, so like, there's lots of things where you can like use machine learning and you'll understand this particular set of alloys, but it's not generalizable to something else. So while we're developing maybe these pie in the sky ideas of finding, better glass formers using a method that we don't understand, we can also try to understand. So I think that's the justification of almost all fundamental research, that it will increase understanding, which will have benefits to the system you're studying and to possibly other fields.
Okay. Can I also, sorry.
Yeah, maybe you can ask.
Okay, so my other question was like, so I'm not familiar with alloys, but I'm wondering like, as you get to like higher order, like number of like different materials in that alloy, is there a point where it becomes like unreasonable, or is it typically like 2 or 3 is considered reasonable? Basically, I'm wondering like, how can you scale this experimental approach up? And is there a point where it's not really useful to know larger, like more complex alloys?
There's definitely a background, that is the background glass variability of like, you just take a random alloy system from like, let's say binary, take a random binary alloy, there's like a background glass variability. Do the same thing for a ternary. You randomly pick a ternary. And the glass variability definitely decreases with the number of components. I mean, the glass variability increases as you increase the number of components. On the flip side, the number of features grows. So when I was talking about, basically in your feature space, you need features for both endpoints. And so there, you could say, well, I'm gonna have 3 features for this endpoint, 3 features for this endpoint. Well, there's also features for the mix.
Right.
Well, then that you have that, it's combinatorial. So you then now have another axis. You have a feature for this endpoint, a feature for this endpoint. So the issue is that you have this dramatic increase in the number of features in your space. So
And you can't-
definitely, if you're going to take a fundamental route, you're going to start with binaries. And I was glad I was able to convince. I think take a standard person in the BMG community, they wouldn't study this system because you're most likely not going to form this mysterious bulk metallic glass that you can now use in cars. The reason why you study binary alloys is because you can start to understand what controls the glass variability in that particular system. That maybe you could then leverage to understand, like ternaries. Are ternaries a bunch of binaries? Or is it something new?
So it's not clear. So basically what you're saying, what my understanding is that it's not clear whether you can consider ternaries to be some like superposition of what you would assume from binaries, it could be something like totally different.
That's right.
Okay.
Okay, do you have a quick question or a long question?
It can be quick.
Yes.
Have you compared how these computational mixing enthalpies compare to like experimental or CalFed values? Have you considered entropy of mixing as a factor?
Yeah, so the entry of the mixing is basically, we incorporate that in the model. So whenever I was talking about epsilon AB, it can be directly related to an entropy of mixing or heat of mixing from experiment. And haven't done much, my understanding of CalFed is it's made basically sort of the equilibrium phase diagrams. I think underlying everything I said is if I could understand the equilibrium phase diagrams, that's a good part of the way to the glass variability. Not quite, but everything I said for equilibrium phase diagrams could be said for what I said you could replace with equilibrium phase diagrams. Could we understand those in terms of a certain set of features? Is a similar problem.
All right, let's conclude the seminar and thanks the speaker again.